Hello. In our last class, we have seen very per unit method for calculation of fault. Today we will solve some problem, and to solve that problem, before that we will review some formula related to per unit system. So Z per unit equals to, we can apply this Z actual value into MVA base by kV base square. One thing we can apply, and another thing, Z per unit equals to Z actual value into MVA base by device own base. MVA of device. It is applicable where the previous and present base kV are same. So we will apply this too. Now take one problem. And one more thing, fault MVA, it is equals to MVA base divided by per unit X equivalent. Per unit X equivalent, and also we know that fault MVA is equal to √3 multiplied by V line voltage at fault point multiplied by fault current. Now, if this line voltage is in kV and fault current in kiloamps, then only it will be fault, its unit will be in MVA. If it is kV and it is in amps, so it will be kVA. Okay. Now, fault, from this we can find out fault current. Fault current will be fault MVA into 1000 divided by √3 V fault in kV, and then it will be in amps. It will be in amps. So now, why this fault MVA and fault current is so important, or why we need to calculate that? Because suppose that this is one power system network, and if fault occurred here, then this is circuit breaker. This circuit breaker must capable the fault power and must capable the fault current passing through this. So, for design point of view circuit breaker, so fault MVA and fault current is very essential. So to design this circuit breaker, we need to calculate this fault current and fault MV. Okay, so take one problem. So I can erase it. I hope you can note it. And another important formula I will write here. That is, if suppose that this Z per unit, it is related to 1 kVA base and 1 kV base. Now, if we want to convert this per unit value with another base quantity, then that is called change of base. For change of base, first case 1 kVA and 1 kV is selected, and next time another kVA and another kV should be selected, and we have to convert this Z per unit from old base to new base, and that is why we can say Z per unit at new base equals to Z per unit at old base multiplied by kV base old divided by kV base new, its whole square, multiplied by MVA base new, MVA base new divided by MVA base old. Okay, we will also use this formula. So take one problem. Note 2 generator to 11 kV 3-phase. Problem is 2 11 kV 3-phase 3000 kVA generators having subtransient reactance of 15% operate in parallel. So two 11 kV 3-phase 3000 kVA generators having subtransient reactance of 15% operating in parallel, and the generators supplying power to a transmission line through a transformer, through a 6000 kVA transformer of ratio 11 kV by 22 kV and having leakage reactance and having leakage reactance of 5%. So all this data are given. Now calculate fault current and fault MVA, that means fault power. If fault, three-phase fault, if three-phase fault occurs at LT and HT side. Now, so now see. So problem is two 11 kV 3-phase 3000 kVA generators having sub-transient reactance of 15% operating parallel. That means these two generators are operating parallel and their reactance it is 15%. It is also 15%, and they are operating parallel and they are supplying a transmission line through this transformer. Transformer rating is 6000 kV, 11 kV oblique 22 kV, and its leakage reactance is 5%. Now we have to calculate the fault. If fault occurred here, that means at LT side. If fault occurred here, at HT side. In two different cases, and the value will be different. So now we'll solve it. I think problem is clear. Two generators, they are working in parallel. They are supplying a transmission line. This is the transmission line through this transformer, and if fault occurred this LT side, what will happen? What will be the fault MVA? What will be the fault current? We have to find out. At the same time, if fault occurred at the HT side, obviously the fault MVA, the fault current will be different, and we have to calculate it. So I think I can erase it. Now, to solve this, we should use, as we know this is transformer, so you have to make one reactance diagram. So reactance diagram, that means it will be like this. It will be same like this. Only this transformer will be replaced by one reactor by one reactor, and first case the fault is here. So this is generator reactance and this is transformer reactance, that means XT and this is XZ. Now we consider for first case, we consider the base kVA, that means base power, base kVA is 6000 kVA, and base voltage at generator rated side, it is 11 kV, and base kV or base voltage at transmission side, it is 22 kV. Here one thing is very important. Whatever may be big the power system network, suppose that here this is generator, then it is step up transformer, this is transmission line, then another secondary transmission line, then it can be load. It is that. If it is 11 kV, it is 400 kV. It is once again it is 400 kV, 132 kV. It is 132 kV, so it is 33 kV, like that. If it is like this, then for entire system, if we choose base kV for the generator, suppose that is 11 kV, due to transformer action here, for this is transmission line 1 and this is transmission line 2. For entire transmission line, the base kV, here it is base kV 11 kV, here the base kV will be 400 kV for entire transmission line, because due to this transformer action. Similarly, for this transmission line 2, entire here the base kV will be 132 kV, here it will be 33 kV. That means the base kV will be differ if there is in transformer. But for the entire network, the base kVA will remain same. So kept in mind, base kVA will remain in same for the entire network, whereas the base kV may differ due to transformer action. I think it's clear. Here, if it is 11 kV, then it can be 400 kV, it can be 132 kV. So base kV here 132 kV, here 400 kV, here 11 kV. It is possible. But here, if it is 10,000 kVA, is base kVA for here, it will be base kVA for 10,000 kVA, it will be base kVA. Even for the load, also the base kVA will be 10,000 kVA. That means entire system base kVA will remain same. Okay. So this is, that means here the base kV in this side, base kV is 22 kV, whereas in this side base kV is 11 kV. And we assume our base kVA is equal to 6000 kVA, that means 6 MVA. Now, per unit reactance of generator equals to actual value. We can apply this, because here we can apply this value. So it is 15%, that means 15 by 1000 into base MVA. Base MVA is 6000, that means 6. Base kVA 60,000, that means it's device kVA, MVA of device, it is 3. So it will be 15 by 100 upon 2. So it will be 0.3 per unit. 0.3 per unit. and xt, and these two generators working in parallel, that means equivalent reactance of these two generators will be 0.3 by 2 per unit, that means 0.15 per unit. Equivalent reactance of these two generators, as these two are in parallel, so it will be 0.3 by 2. You know, same thing are in parallel, then parallel equivalent will be by 2. And per unit reactance of transformer, it is equals to, it is 5%, that means 5 by 100 into its device base kVA 6000 and base kVA its own kVA is also 6000, so it will be 1, so no need to calculate base or equals 6 by 6, so no need to calculate it, so its value will be 0.05 per unit, 0.05 per unit. So for the entire network fault up to here, the X equivalent per unit X reactance equivalent equals to how much? This equivalent reactance, what is this? This is 0.05 per unit, and it is 0.3 per unit, and these two in parallel, that means 0.15 per unit plus 0.05 per unit, that means it is equals to 0.2 per unit. 0.2 per unit. Now base MVA, I have written here base MVA, fault MVA, fault MVA, it is equals to MVA base divided by, I think this formula is already written, by X per unit X equivalent. It is equals to how much? MVA base 6 and per unit it is equal to 0.2, that means 30 MVA, 6 MVA, 30 MVA. So that means if fault occurred at this IST side, the fault MVA will be 30 MVA. And what will we know that? Fault MVA equals to √3 into V line at fault point into I line fault. I line fault. Now, if it is in here, it is fault MVA is how much? So if it is in kiloamps and if it is in kilovolt, then it will be fault MVA. That means if it is, we can I fault, it is equals to fault MVA into 1000, 10 to the 3. It is converted in kilo kVA, fault kVA, and it is √3 into fault line voltage at fault point. Line voltage at fault point, it is 22 kV. 22 kV, and if it is kV and it is kVA, then it will be in amps, and it will comes around 786 amps. And if all the is per unit reactance, that means the current will be 90 degree lagging. 90 degree lag. That means if fault occurred here, the fault MVA for fault fault MVA 30 MVA, and fault current it is equal to 786 amps. Okay, kept in mind. We'll see. Now, if fault occurred here, that means this reactance has no value. Only these two reactants will limit the fault current. Okay. Now this equivalent, if these two, then equivalent will be only 0.15 per unit. It is the equivalent reactance. Then X equivalent will be 0.15 per unit. I think previous thing was clear. And now it will be only this 0.15. And transformer reactance is no more required. So fault MVA, it will be base MVA divided by 0.15 per unit X equivalent, and it will be 40. It will be 40. And if it is 40, then it will be around, that means 40 into 10 to the power 3 divided by root 3. If it is in LT side, it will be 11 kV. It will be 11. It will be around, its value will be around 2100. Its value will be around 2100 ampere. Its anti-degree lagging, 90-degree lag. So if fault occurred at one more thing, if for LT fault MVA for MVA equals to 40 and fault current is equal to how much? 2100 ampere. Now we will see if fault KVA is, if fault KVA is 6, instead of 6 MVA, it can be select as a 300 kVA. That means if it is 3000 kVA, then it will be 3. If it is 3, then everything will be changed, and we will see the value. Fault per unit value will change, obviously. If the base is changed, per unit value will change, but the fault current and fault MVA value will remain same. Whatever base you can select. Even you can select another any arbitrary value. Suppose 10,000 kVA you can select, no problem. In that case, assume it, here it is 3 MVA, so per unit X of generator it is equals to how much? 15%. And base KVA, once again it is base KVA, but base KV for generator side it is 11 kV. Okay, that means for 15%, that means 15 by 1000, 15 by 100, and base KV 11 by 11 whole square, and base KVA 3000 by 3000 whole square. That means it will this by using this here 11. So if fault occurred here, that means here in that case what will happen? Generator reactance, it will be 15 by 1000. 15 by 1000 it will be, because by using this same KVA, same base KV voltage, previous and new, and same MVA, or here it is 3 MVA and its own MVA is also 3. That means it is like that. And if these two generators are in parallel, that means its equivalent is 0.05 per unit. Now, when fault is here, then fault MVA, fault MVA, it is equals to, as per formula, it is MVA base by per unit X equivalent, and it is equals to MVA base, it is equals to 3 divided by 0.075, and it is equals to, once again it will be 40 MVA, 3 MVA, it will be 40 MVA. That means if fault is in LT, in previous case fault MVA was like this, and here it is once again with a new base, another base, not 3000, instead of 6000, it is 3000 is considered, and it is equals to 40. That means base MVA selection is not so important. You can select anyone, but the base MVA will remain same, but the base KVA will differ due to transformer action. Kept in mind, it's very important. At the same time, if you take another problem or like that, you can solve it. And I think this process of solving fault current and fault MVA, it's clear to you. Hope so. Okay, thank you.